Okay, hey everybody. Let me explain something real quick I'm going to do here. As I go through the video, there'll be times when I'm asking you to pause and do some work, just like we would have done in class, where I'd have you guys try some stuff and then we'll talk about it later. So throughout these videos, that's going to occur as well. And it's super important that you do those because that's where you'll start to discover what you were already trying to kind of figuring out and what you kind of didn't really exactly know. It definitely helps you organize and understand a little bit better what it is the lesson is. So I strongly encourage you to do it. I won't know if you actually do it, but I do encourage you to do it. And then other times, because of the way the video is going to go, I'll just be pausing the video myself. I'm going to set up a different scenario and then I'll press play. So it might be kind of herky-jerky, meaning we might go straight from one activity to the next. But it's the most efficient way to do it, I think. Okay, so the first thing I'm going to do is I'm going to kind of summarize or wrap up the lava activity that we did last week or week before last. We're trying to get to that A, right? That was the whole task, was how can we get to the A, or how far away from the A are we? So what I'm going to do is I'm going to just kind of trace here. This is what we're trying to figure out. We're trying to figure out how far it was from there, that A, to this safe side over here, right? So this is where we were standing, or you guys were standing on this side, and that's the A, and here's the lava. And you're trying to find out the distance from that A to your safe side. And I believe there was like a desk or something that was like this, and the front edge of the desk here was the safe side. So technically the desk went out into the lava like that. So this was our safe side over here, and that's kind of where what we had. I think there's probably like another desk on this side or something like that, depending on what your setup was, right? Each group kind of had a little bit different setup, but basically that's what it was. Is we had a safe side here. We're trying to figure out how far it is from this safe side over to that A. And as I mentioned, that there was some estimation that I was allowing, but there's other estimation that I was not allowing. I mean, I wasn't allowing you to estimate, well, I think it's about 7 feet or 9 feet. So that wasn't the estimation that I was allowing. What estimation I would allow is lining things up, because you could get pretty accurate if you use a couple of people to line up, in a line or a sight line. And if you use the string, then you could get very, very close. So, in order to do this, we probably want to try and use our idea of similar figures. Similar triangles would be best. So what we would have to have is, I'm trying to find this distance, all right? So that's not going to be figured out because I can't go into the lava. But what I could figure out is, let's say this was one of those desks. So I could actually measure from, say, here to here if I wanted to. And that distance from here to here would be equivalent to the distance if I was able to measure from there to there. And here's where the estimation was. If you had a person standing down here and they were looking right at the edge of this desk, they could get a pretty good mark as to where that end of that corner was. So they could find something, maybe the windowsill or something on the wall, and say, yeah, that's where this line right here would be equal to that line right there. So let's say we're able to, and we would be able to measure this one, because this is on dry land, or on safe land over here. So we could measure this distance. Let's just say it was 50 inches. So if the distance from here to here is 50 inches, then that means the distance from here to that spot that I visually looked at, it would be 50 inches. Okay? So that part on the wall, or the floor, whatever you were looking at, would be 50 inches, and this part would be 50 inches. Now, if somebody else were to get lined up and say, okay, so I can now take this spot of the wall and line it up with this spot that is the closest to our A. And then you could take, with your sight line somebody line you up. So you got a person over here somewhere looking, okay, they're looking like that, and they're lining it up. And when you get to right here, you grab some of that string that we had, and you now pull the string out like that. You can't pull the string over here because that's the lava, but we could totally pull the string down here, okay? So that's an estimation I would allow. You're using that sight line from this spot on the wall that this person saw, And then this person is, okay, going right through that point, which is the closest point to our A, and now I'm in a straight line here. Now, what I see here then is I could extend this line out, because, you know, somebody else could be looking right here and looking up that way and say, okay, well, I see that this A is lined up with that corner of the table or whatever, and it goes in a straight line like that. And then the only other estimation we would need is that this would pretty much need to be parallel to that wall over there. So this wall right here would be parallel to this one right here. So again, that's an estimation that I think we could get pretty close to. So if these two are parallel, then I know I'm going to have similar figures, because this angle right here and this angle right here are vertical angles. And if that's parallel with that, that makes this red line a transversal. So that means that this angle is an alternating interior angle with that one. So that means those two are similar. And so that means that this triangle, or congruent, excuse me, that means this little triangle is congruent to that big triangle. And so if what I'm trying to find is the distance from here to there, right? If I'm trying to find the distance across that lava, then I need to have corresponding sides. So that side of 50 would correspond with this side. So let's say I measure that and it came out to be 30 inches or whatever. And then this side, I could measure this side right here because it's on safe land. And let's say that that was 40 inches. Well, now, if I know that this one is 40, and I know this one's 30, and I know that one's 50 because I safely measured it over here, and I know that those two are congruent, so that one's 50, then I can set up a proportion that would allow me to solve for that x. So it'd be something like 40 over x is equal to 30 over 50, or however you want to set that up. I'm not going to go and do the math on that because everybody's measurements would have been different, but that's how you would set up. That's what we were going over in the middle. So down here would have been built out of string. So you would have people holding pieces of string on the ground so that you can then measure all of these distances, and then that would be a measurement of, say, one of the tables, or it could be part of the string as well. You could use string on that, but that's how you could figure it out. You get a really close estimate because these sight lines are actually going to be relatively accurate. Okay, so that's kind of wrapping up the lava problem, and now we're going to move on to something else. So I'm going to go ahead and pause the video for a second. Okay, so the next thing is we want to start saying, okay, how could we use this to find heights of other things or distances of other things that we might see out in the world that we don't really want to try and, climb a tree to do or whatever. So here's a pretty typical problem, and I'm going to kind of show you how it works with the, why it works, I should say. So here we have a tree casting a shadow, and we have a person casting a shadow. And assuming it's the same time of day, right? That's kind of important. One can't be at, 2 o'clock in the afternoon and one be at 7 o'clock in the afternoon. It's not going to work. But assuming they're at the same time, then we can use this to find out the height of that tree. All right. So the reason it works is because it's possible for this person, whoever this is, to walk into the shadow of this tree and line it up perfectly so that the tip of his shadow would be right at the tip of the tree's shadow. So I'm not really sure where that point is along here, right? But there is some point where this person could walk into the shadow, and let's say that it's about right there, right? So that person is standing more or less right there. And their shadow is now laying right from here all the way over to there is their head. Okay, so that's their head right there. So their shadow is exactly at the tip of that tree. Now the reason that's important is because over here we have the sun. And the sun is casting down all these rays. And if that person puts their head directly in line with this tip of the shadow right here, their shadow, tip of that shadow, that means that the sun's rays are going just like that. They're going right off the very top of the tree, right off the very top of his head, right to the same spot. And what you might notice that we set up there is 2 embedded triangles. So we have a triangle there, and we have a triangle going through this guy. So now I'm going to draw that same thing down here without the tree and without the guy so that you can just see it a little bit better. So we have the green one representing the tree, like that. And then you have the blue one representing the dude, like that. And then we have the red one going down like this. That's the sun rays. And then on the bottom here, we have the shadow of both of those things. Okay? So you see that we have embedded triangles. The question is, how do we know for sure that these 2 lines are parallel? They would have to be parallel in order for us to know that the small triangle is similar to the large triangle. And the reason we can figure out that they're parallel is because for the most part, people do not walk around at a slant. Maybe when they're walking home from the bars or something, or after tailgating, they might be leaning or slanting or something. But for the most part, we stand at a right angle to the earth. And again, for the most part, trees stand or grow at a right angle to the earth. So if they grow straight up out of the earth and we stand straight up on top of the earth, then we're going to be at right angles. If we're at right angles, then those 2 triangles are going to be similar because they're embedded triangles that are similar and they share an angle. So then we can figure some stuff out. All right. So it's pretty easy to figure out how tall he is. Let's suppose he's 5 feet. Okay. So that dude's 5 feet. That makes this 5 feet, the blue one there. And let's say that he cast a shadow that was 8 feet. So from there to there is 8 feet. Well, then that's from here to here is 8 feet. And then we can easily measure the length of the tree's shadow. Let's say the length of the tree's shadow was 17 feet. All right. So then we could do the length of the tree's shadow is 17 feet like that. And now we have everything we need to set up our proportion so that we can find the height of this tree, which is what we want to know, the height of that tree right there, and that height would be right there. Okay? So now I'm going to set up my proportion of this one. I will go ahead and set the proportion up for. So what I have is I have a shadow. Okay? I have a shadow. That's the things that are here. And then I have the items, the person or the tree, whatever you want to, say. So we have the shadow and the person or the tree. And then we have a small and a big, just like that. Okay. So let's see here. So we have the small shadow is equal to 8. That's the small shadow. And the big shadow is equal to 17. So there's the big shadow. And then the small item or person in this case, the small person, the small item is 5. And the big one we don't know. That's the x. So there's one of my 4 proportions that I could write. At this point, I think we pretty much know how I would solve it. I would go ahead and circle an arrow to show direction of what I'm doing. So I'm going to get 8 times x is equal to 5 times 17. And then I'm going to get 8x is equal to 85. And then I'll divide both sides by 8. And I get x is equal to, and you could leave it 85 over 8, or if you want to make it 10 and 5/8, that's fine with me. All right. And then I guess that would be feet because that's what I measured in. Okay. So this is one of the embedded triangles that we can do. It's very useful. We're going to find a lot of heights just by looking at the shadow of a person, the shadow of an item. I know that I'm 6 feet tall or just a hair under 6 feet tall, so it's pretty easy for me to find the heights of things because I'm 6 feet almost exactly. So I could find my shadow, an object shadow, and I can tell you how high just about anything is, just because I know this embedded triangle will work. All right. Okay, so that's one of the very useful ways we can find the heights of things. This actually is the problem that I mentioned in a couple of my classes, that my dad does it really weird and really hard, and I was calling him an idiot because it's a much easier way of doing it. Unfortunately, because of the coronavirus, I can't share that with you, but this was one of the problems that I was talking about earlier. Okay, I'm going to go ahead and press pause again, and we'll take a look at something else. Okay, so here's the next problem that we're going to do, and here's one where I'd like for you to press pause for a moment and take a look at it, and then get your paper set up, and then we will come back together here in just a second. Okay, so hopefully you've already had a chance to pause and read the problem and get an idea of what we have here. So here's what we got. An alien baby can jump 11 feet during the daytime, except for at noon. At noon, the baby cannot jump at all. How can the alien baby, how can the alien baby and the alien mom figure out for sure if the baby can jump across the river of lava? All right, so again, we got lava going on again. In this case, the mom does not want to be wrong, so she doesn't want to estimate it. She wants to be very, very accurate here, as accurate as possible, to see if her baby can make it across that river. Okay. Now, as you read this, you might have thought there was a couple of facts in there that were kind of weird or interesting, or why would he say that? And sometimes I do throw facts in there that are kind of distractors, but in this case, they actually were a hint on what we're going to use to be very accurate here. And so what you might have noticed is that I talk about the time of day for some reason. I say he can't do it at noon. So why wouldn't the baby be able to jump at noon? Or what does noon have to do with anything? Well, if you think back to the last problem that we just did about the shadows, the shadow at noon potentially would be going straight down, and you can't see a shadow. So you couldn't use a shadow at all to help you set up these similar triangles. So in order for us to use the idea of similar triangles, it either has to be before noon or afternoon, so that we can see the shadows, so that we know that how we can use our similar figures. Okay, now the second thing on this problem is it's actually a combination of the how close to my A am I, and the shadow problem for the tree, the height of the tree that we just did. We're going to kind of use both of those ideas. Clearly, we can't turn this into an embedded triangle because the lava is in the way. But if it's not noon, then that means that the baby is casting a shadow, let's say, like that. Okay, so there's the baby's shadow. Now, the reason that the shadow is important is because, let me back up real quick. What we're trying to figure out is, can the baby jump across here, right? That's the question. Can the baby jump from this side to this side? So I'm going to go ahead and put that in as my X. So we need to be accurate. When we did our how close to the A am I, we estimated a couple of things like, am I parallel? Am I not parallel? Am I lined up exactly in line? So we did some estimating. Here, we don't want to do as much estimating. We want to be as accurate as we possibly can. And since I have the baby on one side and the person on the other side, I can measure things on both sides. The baby could measure things and the mom could measure things. So that's pretty helpful. So what I noticed then is, okay, if the baby measures this part here, and I do that sight line thing like this, then awesome, because the baby can measure that, and then all I have to be able to do is measure on my side. So I do have to make sure that it is parallel to this, right? So this next line that I draw here has to be parallel to that baby's shadow. And the great things about shadows is all shadows are parallel because they're all coming from the sun. So anytime you line up two shadows next to each other, those two shadows are parallel. So literally all you would have to do is to put a stick in the ground like this, put a little stick in the ground, and that stick is going to cast a shadow like this on the ground. Whoops, that's not a very good parallel shadow. And that stick is going to cast a shadow on the ground like that. And whatever that line is, it is going to be parallel to that line is. So these two shadows are going to be parallel, I guarantee it. So it's super simple. The mom could come stand here and measure her shadow. You could put a stick in the ground and measure that shadow. So all I need is anything that would cast a shadow, because that shadow will be parallel to that shadow. And then we know if those two lines are parallel, I'm going to have similar figures. So then I have this distance here, which I can easily measure. So I could measure this distance right here. I could measure this shadow right here. And then I could measure that side over there. So let's just suppose that we measured this shadow as being 3 feet. And we measured this distance here was 7 feet. And the baby's shadow was 5 feet. All right. So the baby's shadow is 5 feet. This stick, whatever it was 3 feet. This distance is 7 feet. So the question is, can the baby jump from here to here if the baby can jump 11? Okay, so now I'm going to go ahead and set it up. So I'm going to have a shadow, right? So we've got shadows again. And then we've got the objects, either the baby or the stick. And then we have, I'm going to call it lava because we have a lava side. And then we have a land side, right? I don't really care what you call them, but I'll have the land side and the lava side. The lava being the one that has the X in it. Okay, so the lava shadow is the baby shadow, right? So the lava shadow is the baby shadow, so that's 5. And the land shadow is the sticks, so that's 3. And then the object on the lava side, that's the baby. I'm sorry, that's the X, that's what we don't know. And then the object on this side is the 7. Which I guess object was kind of a weird name. Maybe I should have called that vertical line, right? I'm going to change it actually to vertical. That makes more sense. So not really the height of the baby or the height of the stick. So I'm going to go vertical line there is better. So this vertical line is the lava vertical line and the land vertical line. Okay. So at this point, I do the same thing every time. I'm going to go like this, circle and arrow, circle and arrow. So I get 7 times 5 is equal to 3 times X, and I followed my arrows. So here I have 35 equals 3X. And then my last step is to divide both sides by 3. So I get X is equal to, and 3 goes into 35, 33, and it doesn't matter what's left over because whatever is left over is too much. Excuse me, it's not 33, it's 11. Nice try. It's 11 and 2/3. And it doesn't matter how much is left over because if it's 1 inch left over, that baby cannot make it because he can only jump 11 feet. So if that baby tries to jump over the llama, it is good night for the alien baby. All right? Okay, so here's a problem where we kind of used both things that we learned. The drawing or creating similar triangles across an area like the lava, and then we also used the shadow, and what the shadow allowed us to do to make sure that we had parallel lines because all shadows are parallel. Okay, so there's 3 different problems that all are like real world problems. I guess maybe aliens and lava jumping is not really real world, but you kind of get the idea how it could be applied. These are super useful skills. We can figure out the distance across things without ever having to try and actually get across them. We can get very, very accurate. just by being able to measure the distances on our side or the safe side of these triangles. Okay, we got one more concept today, and then that's it. Okay, couple more pauses here.